The idea that the concept of a field changed how we understand nature marks one of the deepest turning points in the history of physics. Before fields entered scientific thinking, nature was mostly explained in terms of objects and forces acting directly between them. If an apple fell from a tree, it was because Earth pulled it. If a magnet attracted iron, it was because of some invisible pull between the two. These explanations worked well enough for everyday observations, but they carried a hidden weakness. They never truly explained how one object could influence another across empty space. The universe appeared to allow action at a distance, where effects happened without any clear mechanism in between. For a long time, this mystery was accepted rather than solved. Isaac Newton himself, despite creating the laws of gravity, was uncomfortable with the idea that gravity acted instantly across vast distances. He could describe how gravity worked mathematically, but he admitted he did not know how it was transmitted. This gap between description and understanding remained for centuries. Physics could predict motion with great accuracy, yet it could not explain the medium through which forces operated. Nature seemed to rely on invisible threads connecting objects, threads that no one could see or touch. The introduction of the field concept slowly dissolved this problem. Instead of imagining forces reaching across space like invisible hands, scientists began to think of space itself as something active. When an object exists, it does not merely sit in space, it changes the space around it. That change is what we call a field. Other objects do not feel the influence of the object directly. They respond to the condition of the space they are in. This shift may sound subtle, but it completely rewrote the logic of physical interaction. This new perspective transformed empty space into something meaningful. Space was no longer just a backdrop where events occurred, it became a participant in those events. A field assigns properties to every point in space, even where no particles are present. This means that influence does not leap magically from one object to another. It travels through space step by step. If something changes at one location, that change spreads outward through the field. This idea immediately solved the uncomfortable problem of instant action at a distance. One of the earliest and most powerful successes of this idea appeared in the study of electricity and magnetism. Experiments showed that electric charges affect the space around them, creating electric fields. Magnets do the same, producing magnetic fields. These fields could be mapped, measured, and even visualized using iron filings or test charges. Suddenly, invisible forces became structured patterns filling space. The field was no longer an abstract idea. It was something that could be studied and quantified. The real revolution came when scientists realized that light itself was not a stream of material particles traveling through empty space, but a wave moving through a field. James Clerk Maxwell showed that electric and magnetic fields are deeply connected and can sustain each other as waves. Light turned out to be an electromagnetic wave, a self-propagating disturbance in the electromagnetic field. This discovery changed the nature of reality. Light no longer required a material medium, and empty space no longer needed to be truly empty. The field itself was enough. This new understanding unified previously separate phenomena. Electricity, magnetism, and light were no longer different forces, they were different expressions of the same underlying field. This unification demonstrated the true power of the field concept. It was not just a way to explain forces, it was a framework capable of revealing deep connections in nature that were invisible before. As the field idea matured, it reshaped our understanding of gravity as well. Albert Einstein took the concept to an entirely new level by proposing that gravity is not a force in the traditional sense at all. Instead, massive objects distort spacetime, creating a gravitational field that tells other objects how to move. In this view, planets do not orbit because they are pulled by a distant force. They move along natural paths in curved spacetime. Gravity became geometry, and the field became the very structure of space and time. This was a radical departure from the old picture of the universe. Space and time were no longer rigid and absolute. They could bend, stretch, and ripple. Massive stars and black holes could warp spacetime so strongly that even light could not escape. These ideas were once purely theoretical, but they have since been confirmed by experiments and observations, including the detection of gravitational waves. These waves are literal vibrations of spacetime itself, traveling across the universe and carrying energy through the gravitational field. The concept of a field did not stop evolving with relativity. In the microscopic world of quantum physics, fields became even more fundamental. Quantum field theory revealed that particles are not independent building blocks, but excitations of underlying fields. Every type of particle corresponds to a field that exists everywhere. An electron is a localized vibration of the electron field. A photon is an excitation of the electromagnetic field. Even forces arise from fields interacting with each other. This realization overturned the classical idea that matter is made of tiny solid objects. Instead, matter became a pattern of activity in invisible fields. The universe, at its deepest level, is not made of things but of processes. Fields fluctuate, interact, and exchange energy, and what we observe as particles are just temporary manifestations of those interactions. Perhaps the most profound consequence of this shift is how it redefined emptiness. What we once called empty space is now understood to be filled with fields, even when no particles are present. These fields are never completely still. Quantum fluctuations constantly disturb them, creating brief appearances of energy and activity. The vacuum is not nothing, it is the most dynamic state of all. This new view of nature also changed how scientists think about causality and influence. Information and energy cannot travel faster than the speed set by the fields themselves. This preserves the order of cause and effect and aligns with the principles of relativity. The field acts as the messenger of interaction, ensuring that nature operates through continuous processes rather than mysterious leaps. The field concept also brought elegance and unity to physics. Instead of memorizing countless force laws, scientists could focus on a smaller number of fields and their interactions. Complex behavior emerged naturally from simple underlying rules. This simplicity hinted that fields might be the most fundamental language of the universe. In everyday life, we may not notice fields, but they shape everything we experience. The solidity of matter, the warmth of sunlight, the stability of atoms, and the motion of galaxies all depend on fields. Even your own body exists because of delicate balances between electromagnetic and quantum fields. Without them, atoms would collapse or fly apart, and matter, as we know it, would not exist. Understanding how the field concept changed physics is not just about learning a scientific idea. It is about recognizing a shift in how humans understand reality. Nature is no longer seen as a collection of isolated objects pulling on each other from a distance. It is seen as a continuous, interconnected fabric where space itself carries influence, energy, and meaning. This shift continues to guide modern research. Scientists searching for a deeper theory of everything still rely on fields as their starting point. Whether exploring the early universe, black holes, or the fundamental forces, the language of fields remains central. The idea that once emerged to solve a simple mystery has become the foundation of our understanding of the cosmos. In changing how we understand nature, the concept of a field did more than fix a technical problem. It transformed our worldview. It taught us that reality is not just about objects, but about relationships spread across space and time. It revealed that the universe is not a silent void dotted with matter, but a living structure filled with invisible patterns that govern everything that exists. As this new way of thinking took hold, its influence extended far beyond solving old puzzles. The field concept quietly reshaped how scientists asked questions about nature itself. Instead of focusing only on where objects are and how fast they move, physics began to ask what conditions exist at every point in space and time. This shift turned attention away from isolated events and toward continuous structures. Nature was no longer a set of disconnected interactions, but a smooth web of influences woven through space. One of the most important changes brought by this idea was the way experiments were designed and interpreted. When scientists measured forces, they no longer treated them as direct pushes or pulls between objects. They measured changes in fields. Instruments were built to detect field strengths, directions, and variations. This allowed phenomena to be studied even in the absence of visible matter. Fields could exist where no particles were present, and their effects could still be real and measurable. This perspective also clarified how energy moves through the universe. In older models, energy transfer between objects was often vague. With fields, energy gained a clear location. It could be stored in a field, flow through a field, and change form within a field. When a charged particle accelerates, it does not simply send energy directly to another charge. It disturbs the electromagnetic field, and that disturbance carries energy outward as radiation. Energy became something spread through space, not something jumping between objects. The idea that space itself could hold energy had profound consequences. It meant that space was not passive or neutral. It could be tense, distorted, or excited. In strong gravitational fields, space-time stores enormous amounts of energy. In electromagnetic fields, energy can accumulate and later be released suddenly, as in lightning or electrical discharges. This understanding made natural phenomena more coherent and predictable, grounding them in a single conceptual framework. Fields also provided a new way to think about symmetry and order in nature. Many laws of physics can be expressed as simple statements about how fields behave under changes in position, time, or orientation. These symmetries are not just mathematical curiosities, they reflect deep properties of reality. Conservation laws, such as the conservation of energy and momentum, emerge naturally from the behavior of fields. What once seemed like separate rules became consequences of a unified structure. As physics progressed, the field concept revealed patterns that could not be seen before. Waves, for example, became a universal feature. Sound waves move through air, water waves move across oceans, and electromagnetic waves travel through space. Different phenomena, same underlying idea. A field can vibrate, and those vibrations carry information. This insight allowed scientists to predict new effects, such as radio waves, long before they were experimentally detected. Fields did not just explain known facts, they pointed toward discoveries waiting to be made. Another profound change came in how scientists thought about cause and effect. In the field view, causes do not act instantly across space. They propagate through fields at finite speeds. This preserved a logical structure to the universe. Events unfold in a sequence, with influences spreading outward over time. This idea fit perfectly with the principles of relativity and reinforced the notion that nature has a built-in speed limit. Fields became the guardians of causality. The concept of a field also reshaped philosophy. It challenged the intuition that reality must be made of solid, tangible things. Fields are real, yet invisible. They cannot be grasped, yet they govern everything. This forced a rethinking of what it means for something to exist. Reality became less about substance and more about structure and interaction. What matters is not what things are made of, but how fields behave and relate to one another. This philosophical shift influenced how scientists viewed knowledge itself. Instead of asking for mechanical pictures of every process, physics became comfortable with abstract descriptions that still produced accurate predictions. Fields may not be visual in the everyday sense, but they are precise, testable, and deeply explanatory. This balance between abstraction and reality became a hallmark of modern science. In education and research, the field concept unified diverse areas of physics. Mechanics, electromagnetism, optics, thermodynamics, and quantum theory all began to speak a common language. Students learned to see connections where earlier generations saw separate topics. This unity made physics more powerful, allowing insights from one area to inform progress in another. The technological impact of this shift cannot be overstated. Modern technology is built on an understanding of fields. Radios, televisions, mobile phones, and satellites all rely on electromagnetic fields. Medical imaging techniques use controlled fields to peer inside the human body. Even computing depends on manipulating fields at microscopic scales. None of this would be possible without the conceptual leap that transformed space into an active medium. On the cosmic scale, fields help us understand the large-scale structure of the universe. Galaxies form and evolve under the influence of gravitational fields. Cosmic radiation travels through space as disturbances in fields that have existed since the early universe. By studying these fields, scientists reconstruct the history of the cosmos, learning how it expanded, cooled, and formed the structures we see today. The field concept also reshaped humanity's place in the universe. It revealed that we are not separate from our surroundings. Our bodies, thoughts, and technologies are all patterns within fields that stretch across the universe. The same electromagnetic field that binds atoms in your hand also carries light from distant stars. This continuity creates a sense of deep connection between the human scale and the cosmic scale. Perhaps most importantly, the idea of a field taught scientists humility. It showed that intuition based on everyday objects can be misleading. Nature does not have to conform to common sense to be real. Fields behave according to precise laws, even if they defy simple visualization. Accepting this allowed physics to move beyond outdated assumptions and explore deeper layers of reality. Today, as scientists search for even more fundamental theories, the concept of a field remains central. Whether studying dark energy, quantum gravity, or the origins of the universe, researchers continue to rely on fields as the primary actors. The details may change, but the core idea endures. Space is active, structured, and capable of shaping everything within it. The realization that a simple idea could change how we understand nature is itself a lesson. Progress in science does not always come from discovering new objects. Sometimes it comes from changing how we think about what is already there. By recognizing fields as fundamental, physics moved from a world of mysterious distant forces to a universe of continuous, connected influence. In the end, the field concept did not just improve equations or predictions. It changed the story we tell about reality. Nature became a living tapestry of invisible influences, stretching from the smallest scales to the largest. This story continues to evolve, but its foundation remains the same. Understanding fields is understanding how nature speaks, how it connects every point in space, and how a single idea can reshape our view of the universe forever. For much of human history, the natural world was understood through direct contact and visible interaction. When one object moved another, it was because it pushed it, pulled it, or struck it. This way of thinking worked perfectly for everyday experiences. A hand moves a stone, the wind bends a tree, fire heats metal. Cause and effect were clear because contact was visible. But as scientists began to study gravity, electricity, and magnetism, they encountered a serious problem. These forces seemed to work without touch. Objects influenced each other across empty space, and no one could see how. This led to the idea known as action at a distance. According to this view, one object could directly affect another object, no matter how far apart they were, without anything existing in between. The Earth could pull the Moon, the Sun could hold planets in orbit, and a magnet could attract iron filings through empty space. Although this idea allowed scientists to calculate motion accurately, it left a deep conceptual gap. How could influence travel through nothing? What carried the force from one place to another? Even the greatest scientists felt uneasy about this explanation. The mathematical predictions were correct, but the physical picture felt incomplete. Action at a distance seemed almost magical. It suggested that nature allowed objects to communicate instantly across space, ignoring distance as if it did not matter. This conflicted with intuition and raised troubling questions about causality and realism. The problem became more serious as experimental discoveries advanced. Electrical and magnetic effects showed clear patterns in space. Iron filings around a magnet arranged themselves in smooth curves. Electric charges influenced nearby charges more strongly than distant ones. These patterns suggested that something structured existed in the space around objects. Space did not appear to be empty after all. It behaved as if it had properties. The field concept emerged as a response to this confusion. Instead of imagining objects directly acting on each other across emptiness, scientists proposed that objects modify the space around them. That modification is what we call a field. Once a field exists, any other object entering that space responds to the field locally, at its own position. Influence no longer jumps across distance, it moves through space. This difference may seem subtle at first, but it changes everything. In the action at a distance view, the cause and effect are separated by space but linked instantly. In the field view, cause and effect are connected continuously. A source creates a field. The field exists everywhere around it. Another object feels the effect only because it is located where the field has a certain value. Nothing needs to reach out or pull across space. This new picture made interactions more physical and intuitive. A field can vary from point to point. It can grow stronger or weaker with distance. It can change over time. Most importantly, changes in a field do not happen everywhere at once. They propagate. If a charge moves, the electromagnetic field around it changes, and that change spreads outward at a finite speed. This replaced instant influence with a realistic process. The difference becomes especially clear when thinking about motion and delay. If action at a distance were true in its pure form, then moving an object would instantly affect everything connected to it, no matter how far away. But experiments showed that electromagnetic signals travel at a specific speed, the speed of light. This fact could not be explained by direct action at a distance. The field idea, however, naturally explained it. Fields carry changes through space at limited speeds. This insight transformed the meaning of empty space. Space was no longer a void separating objects. It became a medium that could carry influence, not a material medium like air or water, but a physical structure capable of holding values, storing energy, and transmitting change. Space became active rather than passive. One of the most powerful advantages of the field picture is locality. In physics, locality means that objects are affected only by what is happening at their own position in space and time. Fields obey locality. A particle responds only to the field where it is, not to distant objects directly. This principle brought clarity and consistency to physical laws and aligned perfectly with later developments in relativity. The contrast between the two views also affected how scientists thought about explanation itself. Action at a distance described what happens but not how it happens. Fields explained how influence is structured and transmitted. They offered a mechanism without requiring invisible strings or instant connections. This made physical laws more satisfying and conceptually complete. Another key difference lies in predictability and structure. Fields can be visualized, mapped, and mathematically analyzed across space. Scientists can calculate field strengths, directions, and variations at every point. This spatial structure reveals patterns that action at a distance theories could never show. Instead of focusing only on pairs of objects, physics could now study entire regions of space. This shift also changed experimental practice. Measuring forces directly between objects became less important than measuring fields themselves. Instruments were designed to probe field values. Test charges, sensors, and detectors allowed scientists to observe how fields behaved independently of specific interactions. This opened the door to new discoveries. The field approach also resolved contradictions between different forces. Under action at a distance, each force seemed to require its own unique explanation. Gravity acted one way, electricity another, magnetism another. Fields provided a unifying language. Different forces could be described as different fields, each with its own rules but sharing a common conceptual framework. Perhaps the most dramatic demonstration of the difference between these two ideas came with waves. In the action at a distance picture, waves are difficult to explain. What is waving if nothing exists between objects? Fields solve this immediately. A wave is simply a changing field that propagates through space. light became understandable not as a mysterious influence, but as a wave in the electromagnetic field. This also clarified why disturbances take time to travel. When the sun emits light, the electromagnetic field near the sun changes. That change spreads outward through space. It takes time to reach Earth. Nothing leaps instantly across the gap. The delay is not a flaw but a fundamental feature of reality. As physics moved forward, the field concept proved essential for understanding relativity. The idea that nothing can travel faster than light depends on fields transmitting influence at finite speeds. Action at a distance would violate this principle. Fields preserved causality, ensuring that causes precede effects in all frames of reference. In the quantum world, the distinction became even sharper. Action at a distance could not handle the probabilistic nature of microscopic events. Fields, however, could be quantized. They could fluctuate, exchange energy, and produce particles. This made them suitable for describing nature at its deepest level. The emotional impact of this shift should not be underestimated. Action at a distance felt mysterious and unsettling. Fields replaced mystery with structure. They did not eliminate wonder, but they grounded it in a framework that could be tested and refined. Nature became intelligible in a deeper way. This change also influenced philosophy. Reality was no longer a collection of isolated objects sending invisible commands across emptiness. It became a continuous whole, where space itself participates in physical processes. The universe gained coherence. Everything became connected through fields that fill all of space. Understanding the difference between action at a distance and fields is essential because it shows how scientific progress often works. Old ideas are not discarded because they fail completely, but because a better framework explains more with fewer assumptions. Action at a distance described effects, fields explain their origin. By adopting the field view, physics gained clarity, unity, and predictive power. Space stopped being a passive container and became an active element of reality. Influence stopped being magical and became physical. This single conceptual shift laid the groundwork for modern science and changed forever how we understand interaction, causality, and the nature of the universe itself. As the field-based view replaced action at a distance, its deeper consequences slowly became clear. This was not merely a technical improvement in equations, but a fundamental change in how reality was imagined. The universe no longer consisted of isolated objects interacting mysteriously across empty gaps. Instead, it became a continuous fabric in which influence flows smoothly from place to place. This change brought a sense of physical realism that earlier theories lacked. One of the most important outcomes of this shift was the redefinition of interaction itself. In the field picture, interaction is no longer a direct relationship between two distant objects. It is a local process. An object creates a condition in space, and another object responds only to the condition at its own location. This local response eliminates the need for hidden connections across space. Every effect has a nearby cause, carried step by step through the field. This idea transformed the understanding of time in physics. Under action at a distance, time played little role in how forces operated. Effects could occur instantly, ignoring delays. Fields reintroduced time as a fundamental element. Changes take time to propagate. Signals spread outward at finite speeds. This made time inseparable from interaction and aligned physics with the observable behavior of the universe. The field concept also clarified the role of boundaries and regions in space. Instead of focusing only on objects, physicists could analyze what happens in the space between them. Fields could be strong in one region and weak in another. They could concentrate around certain configurations and spread out in others. This regional view allowed scientists to understand stability, confinement, and structure in nature. Another major consequence was the way momentum and energy were understood. In the field picture, energy does not belong exclusively to objects. It can exist in space itself. A stretched or distorted field stores energy. When the field relaxes or changes, that energy can be released and transferred. This resolved long-standing puzzles about how energy moves during interactions, especially in electromagnetic processes. The recognition that fields carry momentum was equally important. When a field changes, it can push back on the objects that created it. This mutual exchange ensures that conservation laws remain valid. Momentum is not lost or gained mysteriously. It flows through the field. This idea strengthened the internal consistency of physical laws and removed ambiguities that had troubled earlier theories. As fields became central, mathematical descriptions of nature grew more powerful and unified. Instead of separate force laws for each pair of objects, scientists used field equations that applied everywhere. These equations described how fields are generated, how they evolve, and how they influence matter. From these few equations, a vast range of phenomena could be derived. This economy of explanation was one of the greatest strengths of the field approach. The field view also changed how scientists dealt with complexity. In systems with many interacting parts, action at a distance becomes unwieldy. Every object interacts with every other object, leading to overwhelming calculations. Fields simplified this. Once the field is known, the behavior of any object can be determined locally. This made it possible to study complex systems such as plasmas, weather patterns, and astrophysical environments. In technology, the field concept proved indispensable. Communication systems rely on the controlled generation and detection of electromagnetic fields. Power grids operate by managing fields that distribute energy across vast regions. Medical technologies use fields to probe, image, and treat the human body. None of these applications would make sense under a pure action, at a distance framework. The field perspective also reshaped scientific intuition. Students and researchers learned to visualize fields as lines, surfaces, and flows. These visual tools made abstract ideas tangible and guided experimental design. Even though fields are invisible, their patterns became familiar and meaningful. This helped bridge the gap between mathematics and physical insight. At a deeper level, fields influenced how scientists thought about causality and responsibility in nature. Effects are not blamed on distant objects acting mysteriously. They are traced to local conditions and their evolution over time. This strengthened the idea that the universe is governed by consistent rules that apply everywhere, without exceptions or shortcuts. The contrast between fields and action at a distance also highlighted the importance of humility in science. The older view was not wrong in its predictions, but it was incomplete in its understanding. The field concept showed that deeper explanations often require abandoning comfortable intuitions. What seems obvious at one stage of knowledge may later appear crude or misleading. In the quantum domain, the rejection of action at a distance became even more significant. Although quantum mechanics introduces strange correlations, the fundamental interactions are still mediated by fields. Even when particles appear to influence each other in unexpected ways, the underlying framework remains field-based. This preserves a coherent structure beneath the apparent strangeness. Fields also provided a bridge between classical and modern physics. They allowed older theories to be extended rather than discarded. Classical fields evolved naturally into quantum fields. Relativistic fields replaced Newtonian concepts without breaking continuity. This smooth transition demonstrated the flexibility and depth of the field idea. As research pushes toward understanding gravity at the quantum level, the field concept remains central. Scientists continue to debate the nature of space-time and its possible quantum structure, but the language of fields persists. Even when theories change, the idea that influence is carried by space itself endures. Perhaps the most lasting impact of replacing action at a distance with fields is how it changed our mental image of the universe. Space is no longer an empty gap between objects. It is a dynamic arena filled with structure and activity. Objects are not isolated actors but participants in a continuous network of influence. This shift encourages a more holistic view of nature. Nothing happens in isolation. Every event is part of a broader pattern extending through space and time. Fields connect the smallest particles to the largest cosmic structures. They weave the universe into a single, coherent whole. In the end, abandoning action at a distance was not just a technical refinement. It was a philosophical transformation. It taught us that explanations in physics must respect locality, continuity, and causality. By embracing fields, science moved closer to a picture of reality that is both more accurate and more profound. The universe became intelligible not as a collection of distant interactions, but as a living fabric where every influence travels through space, leaving no place truly untouched. Invisible forces have always fascinated human beings because they shape the world while remaining hidden from direct sight. Long before science could explain them, people observed that stones fall, compasses point north, lightning strikes, and objects can attract or repel each other without touching. These effects were undeniable, yet their causes were mysterious. What connects a planet to its star, a magnet to a piece of iron, or a charged object to another across empty space? The concept of fields emerged as the key that unlocked these mysteries, transforming invisible forces into understandable physical realities. Gravity is perhaps the most familiar of these forces, yet for centuries it was also the most puzzling. Objects fall toward Earth, and planets move in graceful paths around the Sun. Early explanations described gravity as a force that acts directly between masses. While this description worked mathematically, it left a troubling question unanswered. How does one mass know that another mass exists far away? The field concept answered this by proposing that every mass changes the space around it. This change is the gravitational field. An object does not feel the distant mass directly. It responds to the local structure of space shaped by that mass. This idea reshaped gravity from a mysterious pull into a property of space itself. Wherever there is mass, there is a gravitational field extending outward. The strength of this field depends on distance and mass, and its presence can be measured by observing how objects move. When you drop a stone, it is not Earth pulling it through nothingness. The stone simply follows the natural path defined by the gravitational field at that location. Gravity becomes less like a force reaching out and more like a guide shaping motion. Electricity introduced an even richer picture of fields. When scientists studied electric charges, they discovered that charged objects influence their surroundings. A positive or negative charge creates an electric field in the space around it. This field exists whether or not another charge is nearby. If a second charge enters that space, it experiences a force because it interacts with the electric field at its position. The interaction is local, not distant. What made electric fields especially powerful was their measurability. Scientists could map them using test charges and observe how their strength and direction changed throughout space. These maps revealed smooth, continuous patterns, proving that the influence of a charge is not confined to the object itself, but distributed throughout the surrounding space. Electric fields turned invisible forces into visible structures, at least conceptually. Magnetism deepened this understanding further. Magnets create magnetic fields that extend far beyond their surfaces. Iron filings sprinkled around a magnet trace elegant curves, revealing the shape of the magnetic field. These patterns show that space around a magnet is organized, structured, and active. The magnet does not need to touch iron to influence it. The magnetic field already fills the space between them. The unification of electricity and magnetism marked one of the greatest triumphs of the field concept. Scientists discovered that changing electric fields produce magnetic fields and changing magnetic fields produce electric fields. This interdependence meant that electricity and magnetism were not separate forces but two aspects of a single electromagnetic field. This realization explained why light exists. Light is not a material substance traveling through space. It is a wave of oscillating electric and magnetic fields moving together. This understanding resolved centuries of confusion. Light no longer required an invisible medium to carry it. The electromagnetic field itself was enough. Empty space became capable of supporting waves. Fields were no longer just tools for describing forces, they became the carriers of energy and information. Fields also explained why these forces behave the way they do with distance. Gravitational and electric fields weaken as you move farther from their sources. This gradual change makes sense in the field picture because the influence spreads out through space. There is no sudden cutoff, only a smooth variation. This continuity could never be explained by direct action at a distance without invoking mysterious rules. Another crucial insight was that fields can exist independently of their sources. Once created, a field can propagate through space on its own. When a charged particle accelerates, it sends ripples through the electromagnetic field. These ripples travel outward as radiation. The source does not need to remain in contact with the effect. The field carries the influence forward in time and space. The field explanation also brought clarity to energy transfer. Energy is stored in fields. A strong electric field contains energy, just as a stretched spring does. When the field changes, that energy can be released, transferred, or transformed. This idea unified mechanical energy and electromagnetic energy under a single principle. Energy became something that exists not only in objects but in space itself. Gravity, electricity, and magnetism may seem different in everyday experience, but the field concept revealed their deep similarities. All three involve sources that shape space around them. All three act locally through fields rather than directly across distances. All three allow energy and influence to move through space in a continuous way. This unification simplified physics and revealed hidden order in nature. The predictive power of fields further strengthened their importance. By understanding the structure of a field, scientists could predict how objects would behave without directly calculating forces between every pair of objects. This was especially important in complex systems with many interacting parts. Fields provided a way to manage complexity and extract meaningful patterns. Fields also explained why invisible forces obey strict limits. Changes in fields propagate at finite speeds. This ensures that effects do not occur instantaneously. It preserves causality, meaning causes come before effects. This idea became essential in modern physics, especially in theories of relativity, where the speed of light sets a universal limit for information transfer. The success of fields in explaining invisible forces changed scientific intuition. Space was no longer empty. It was filled with structure, energy, and potential. Forces were no longer mysterious pulls or pushes. They were manifestations of how space responds to matter and charge. This view replaced mystery with mechanism without removing wonder. Even today, when people feel gravity, use electricity, or observe magnetic effects, they are interacting with fields. These fields operate silently and invisibly, shaping motion, powering technology, and organizing matter. The lights in a city, the signals in a smartphone, and the stability of atoms all depend on fields behaving exactly as predicted. Understanding invisible forces through fields also changed how humans see their place in the universe. We are not separate from these forces, we exist within them. Our bodies, our tools, and our planet are all embedded in gravitational and electromagnetic fields that extend across the cosmos. The same fields that guide galaxies also govern the smallest interactions in atoms. By explaining invisible forces in terms of fields, physics achieved a deeper level of clarity. What once seemed like magic became structure. What once seemed like emptiness became active space. Fields turned the unseen into the understandable, revealing that the universe operates not through mysterious distant actions, but through continuous patterns that fill every corner of reality. As the field explanation of invisible forces matured, it began to reveal layers of meaning far beyond the original problems it was meant to solve. Gravity, electricity, and magnetism were no longer isolated phenomena with separate rules. They became examples of a single principle: space itself can be shaped, and that shape determines how matter and energy behave. This realization gave physicists a new sense of unity and direction. One of the most important consequences of this understanding was the realization that fields are not just mathematical tools, but physical entities with real effects. They can be detected, measured, and manipulated. Instruments respond directly to fields, not to distant objects. This reinforced the idea that fields are as real as matter itself, even though they are invisible. The ability of fields to exist independently of their sources further strengthened this view. A star may collapse, a charge may stop moving, but the disturbances they created in their surrounding fields can continue traveling long after. Light from distant galaxies reaches us millions of years after it was emitted. Gravitational waves pass through Earth long after the cosmic events that produced them. Fields carry history across the universe. This also changed how scientists think about stability and change. A stable configuration in nature often corresponds to a stable field arrangement. Atoms remain intact because electric fields balance attractive and repulsive influences. Planets maintain their orbits because they move within stable gravitational fields. When field configurations change suddenly, dramatic events occur, such as electrical discharges or cosmic explosions. The field concept also deepened understanding of interaction strength. Forces do not act equally everywhere. Fields have intensity and direction that vary from place to place. This variation explains why forces weaken with distance and why direction matters. An object responds not only to the presence of a field, but to its precise structure at that point in space. As knowledge advanced, scientists discovered that fields can interact with each other. Electromagnetic fields can influence charged particles, which in turn modify the fields. Gravitational fields interact with energy itself, including the energy stored in other fields. This self-consistency creates a dynamic feedback system where matter and fields continuously shape one another. This interplay became central to modern cosmology. The large-scale structure of the universe is governed by gravitational fields interacting with matter and radiation. Galaxies form where gravitational fields concentrate matter. Cosmic expansion influences how fields evolve over time. By studying these interactions, scientists reconstruct the story of the universe from its earliest moments to the present day. Fields also changed how scientists interpret motion. Motion is no longer simply movement through empty space. It is movement through structured space. An object's path depends on the fields it encounters. This view dissolves the sharp boundary between force and geometry, especially in the case of gravity, where motion becomes a response to the curvature of space-time. In everyday technology, the field concept became indispensable. Electrical devices operate by shaping electric and magnetic fields. Communication depends on carefully controlled electromagnetic waves. Sensors and detectors rely on field interactions at microscopic levels. None of this would be understandable without treating fields as real, physical components of nature. The educational impact of this shift was equally profound. Learning physics became less about memorizing formulas and more about understanding patterns. Students trained to think in terms of fields developed intuition about how systems behave even before performing calculations. Fields provided a mental map of physical reality. At a philosophical level, fields challenged the traditional notion that reality must be made of tangible objects. Fields are not substances in the classical sense, yet they have measurable effects. This forced a redefinition of what it means for something to exist. Existence became linked to influence and interaction rather than solidity. This shift also influenced debates about determinism and uncertainty. Fields evolve according to laws, but in quantum theory they fluctuate unpredictably. This blend of order and uncertainty reflects the deep structure of reality. Fields follow rules, yet they allow for creativity and randomness at fundamental levels. The explanation of invisible forces through fields also bridged the gap between the microscopic and the cosmic. The same principles that govern electric fields in atoms also govern electromagnetic radiation across galaxies. Gravitational fields shape both falling apples and the motion of galaxy clusters. This continuity suggests a universe built on simple, universal ideas. Fields also helped scientists confront the limits of observation. Even when particles cannot be directly seen, their fields can be detected. This allows knowledge to extend beyond direct sensory experience. Physics becomes a way of seeing the invisible through its effects. As research moves forward, fields remain at the heart of unanswered questions. Dark energy, dark matter, and quantum gravity are all framed in terms of fields or modifications of field concepts. Even when theories are incomplete, the language of fields continues to guide exploration. Perhaps the most lasting impact of explaining invisible forces with fields is how it reshaped human imagination. The universe is no longer a silent void filled with isolated objects. It is an active, interconnected whole, alive with invisible patterns that govern every motion and interaction. Fields connect everything, from the smallest particle to the largest cosmic structure. This perspective invites a sense of unity and coherence. Nothing exists in isolation. Every object, every event is embedded in a web of fields that extend across space and time. Understanding fields is therefore not just about physics. It is about recognizing the deep interconnectedness of reality itself. One of the most powerful insights brought by the concept of fields is the realization that fields are not just passive backgrounds for forces, but active carriers of energy and information throughout the universe. This idea fundamentally changed how scientists understand motion, communication, and the flow of influence in nature. Energy does not simply jump from one object to another, and information is not transmitted by mysterious instant signals. Instead, both are transported continuously through fields that fill space. Before this understanding, energy was mostly associated with objects. A moving object had kinetic energy, a lifted object had potential energy, and a heated object contained thermal energy. Space itself was considered empty and irrelevant to energy storage. The field concept overturned this assumption. Scientists discovered that energy can exist in space itself, embedded in the structure of a field. A strong electric field, for example, contains energy even if no charged particles are moving through it. This was a radical and transformative idea. Consider an electric field created between two charged plates. Even if nothing moves, energy is stored in the space between them. When the field changes, that stored energy can be released, transferred, or converted into other forms. This showed that space is not empty but capable of holding real, measurable energy. The same is true for magnetic fields. Energy is distributed throughout the region where the field exists, not confined to the objects that created it. This understanding clarified how energy travels. When a charged particle accelerates, it does not send energy directly to another particle far away. Instead, it disturbs the electromagnetic field around it. That disturbance propagates outward as a wave, carrying energy through space. Light is the most familiar example of this process. It is energy traveling through the electromagnetic field, moving at a fixed speed and delivering energy wherever it is absorbed. Fields also carry momentum, which means they can exert pressure and cause motion. Light pushing on solar sails, radiation pressure affecting dust in space, and electromagnetic forces acting on antennas are all examples of momentum being transferred through fields. This confirmed that fields are not abstract ideas but physical entities capable of interacting with matter in tangible ways. The role of fields as carriers of information is equally important. Information about changes in a system spreads through fields. When the sun emits light, it encodes information about the sun's temperature, composition, and motion into disturbances of the electromagnetic field. When those disturbances reach Earth, telescopes decode that information. In this way, fields become messengers, carrying signals across enormous distances. This idea applies not only to light but also to gravity. Gravitational waves are ripples in spacetime itself, produced by violent cosmic events such as colliding black holes. These waves carry information about their sources, traveling across the universe and reaching detectors on Earth. Without the field concept, such phenomena would be impossible to explain. Gravity would remain a silent, instantaneous pull with no way to transmit information. The finite speed at which fields carry energy and information is crucial. Changes in fields do not occur everywhere at once. They propagate. This ensures that cause and effect remain ordered in time. Information cannot travel faster than the field allows. This principle protects causality and underpins modern physics, especially theories of relativity. Fields also allow energy and information to spread out, interact, and interfere. Waves in fields can overlap, combine, or cancel each other. This explains phenomena such as interference patterns, resonance, and signal modulation. Modern communication technologies rely entirely on this behavior. Radio, television, mobile networks, and satellites all function by encoding information into controlled disturbances of electromagnetic fields. Another profound consequence is that energy conservation becomes clearer and more complete. Energy lost by an object is not destroyed, it flows into the surrounding field. When an antenna emits a signal, energy leaves the antenna and enters the electromagnetic field, spreading outward. Accounting for energy in fields ensures that conservation laws hold exactly, without mysterious losses. At a deeper level, the idea that fields carry energy and information blurs the boundary between matter and space. Space becomes active, capable of storing, transmitting, and transforming physical quantities. Matter interacts with fields, but fields also exist independently. This mutual relationship defines the structure of reality. In the quantum domain, this role of fields becomes even more fundamental. Particles themselves are excitations of fields, meaning that energy and information are inseparable from field behavior. Every interaction is a rearrangement of energy within and between fields. This makes fields the ultimate carriers of all physical processes. Understanding fields as carriers of energy and information reveals a universe that is continuously communicating with itself. From the smallest atomic transition to the largest cosmic explosion, fields transmit influence across space and time. Nothing happens in isolation. Every event sends ripples outward, carried by fields that connect all parts of reality. This insight reshapes how we see the universe. It is not a collection of silent objects separated by emptiness, but a dynamic network of fields constantly exchanging energy and information. Fields are the invisible highways of the cosmos, ensuring that everything that happens leaves a trace, travels outward, and becomes part of the ongoing story of the universe. Modern physics is built upon the idea of fields, and without this concept, the theories that describe reality at its deepest levels would simply not exist. From the vast scales of the universe explained by relativity to the microscopic world revealed by quantum theory, fields form the common foundation. They provide a single language that allows physicists to describe motion, forces, matter, energy, and even spacetime itself in a unified and consistent way. In the theory of relativity, fields fundamentally redefine gravity. Instead of treating gravity as a force pulling objects toward one another, relativity describes it as a manifestation of spacetime geometry. Mass and energy shape spacetime, and that shape determines how objects move. This geometric structure is itself a field, existing everywhere and evolving over time. Planets orbit stars not because they are pulled by an invisible force, but because they follow the natural paths defined by the curved spacetime field around massive bodies. This view solved problems that classical gravity could not address. It explained why gravity affects light, why time flows differently in strong gravitational fields, and why extreme objects like black holes exist. All of these phenomena arise naturally once gravity is understood as a field rather than a simple force. Even gravitational waves, ripples in spacetime itself, are predicted and observed as traveling disturbances in this field. These waves carry energy and information across the universe, confirming that spacetime is active and dynamic. While relativity governs the large-scale structure of the cosmos, quantum theory reveals a very different but equally field-based picture at small scales. In quantum physics, particles are no longer treated as tiny solid objects. Instead, every type of particle corresponds to a quantum field that exists throughout space. An electron is not a fundamental object moving through emptiness, it is a localized excitation of the electron field. The same is true for quarks, photons, and all other particles. Quantum field theory combines quantum mechanics with the field concept to describe how particles are created, destroyed, and interact. Interactions occur when fields influence one another, exchanging energy and momentum. Forces arise because fields couple together in specific ways. What we perceive as particle collisions are actually interactions between vibrating fields. This framework explains why particles can appear and disappear, why interactions are probabilistic, and why the vacuum itself is active. Even when no particles are present, quantum fields still fluctuate. Empty space is filled with restless activity, constantly producing brief disturbances that influence measurable phenomena. This explains effects that would be impossible under classical ideas of emptiness. Fields also unify forces in modern physics. Electromagnetism is described by a single field that accounts for electric and magnetic effects. The weak and strong nuclear forces are also described by their own quantum fields. Together, these form the basis of the Standard Model of particle physics, one of the most successful theories ever created. Its predictions have been confirmed with extraordinary precision, all relying on the behavior of fields. Another crucial role of fields in modern physics is symmetry. Many fundamental laws are defined by how fields behave under transformations such as rotations, shifts in time, or changes in reference frame. These symmetries are not just mathematical conveniences, they reflect deep truths about nature. Conservation of energy, momentum, and charge emerge naturally from the symmetries of fields. This makes fields the source of both forces and conservation laws. The field concept also allows physicists to bridge different scales of reality. The same principles that govern quantum fields inside atoms also apply to cosmic fields shaping galaxies. This continuity suggests that nature operates according to universal rules, regardless of scale. Fields provide the link between the smallest and largest structures in the universe. Despite its success, modern physics still faces unanswered questions, and fields remain central to those mysteries. Scientists continue to search for a theory that unifies gravity with quantum fields. Dark matter and dark energy, which dominate the universe, are often described in terms of unknown fields or modifications of existing ones. Even when answers are uncertain, the field framework remains the starting point. Perhaps the most profound impact of fields in modern physics is how they change our understanding of reality. Reality is no longer seen as made of objects first and interactions second. Instead, fields come first, objects emerge from fields, interactions are field dynamics, and space itself is a structured, active entity. This view replaces a static universe of things with a dynamic universe of processes. In this modern picture, the universe is a vast network of interacting fields, continuously evolving and exchanging energy. From the bending of spacetime to the flicker of quantum fluctuations, fields govern everything that exists. They are not merely mathematical tools, but the deepest expression of how nature works. One of the most radical ideas introduced by modern physics is that particles are not the fundamental building blocks of reality in the way we once imagined. Instead, particles are better understood as excitations or vibrations of underlying fields that exist everywhere in space. This shift completely transformed how scientists think about matter, identity, and existence at the deepest level. For a long time, particles were pictured as tiny solid objects, like miniature balls moving through empty space. This picture worked well for explaining many observations, but it began to break down as experiments probed smaller and smaller scales. Particles behaved in ways that no solid object could. They appeared and disappeared, acted like waves, and sometimes existed in multiple states at once. These strange behaviors demanded a new framework. The field concept provided that framework. In modern physics, every type of particle is associated with a specific field that fills all of space. The electron field, for example, exists everywhere, even in regions where no electrons are detected. An electron is not something separate from this field. It is a localized disturbance, a small vibration in the electron field. When the vibration fades, the particle effectively disappears. This idea explains why particles of the same type are truly identical. All electrons have exactly the same mass, charge, and behavior because they are excitations of the same underlying field. They are not individual objects with separate identities. They are expressions of a single universal field. This insight solved a deep mystery that classical physics could not address. Understanding particles as field excitations also clarifies particle creation and annihilation. In high-energy environments, such as particle accelerators or the early universe, energy can be converted into field excitations. New particles appear because fields are energized. Conversely, particles can disappear when their energy is transferred back into fields. This process follows precise rules and conservation laws, all governed by field interactions. The wave-like behavior of particles also becomes natural in this picture. Since fields can support waves, their excitations naturally exhibit wave properties. Interference, diffraction, and uncertainty are no longer strange anomalies, they are expected features of vibrating fields. The dual nature of particles as both waves and particles is unified under a single explanation. This view also changes how interactions are understood. Forces between particles are not direct pushes or pulls. They occur because fields interact with one another. When an electron repels another electron, it is because their fields influence each other through the electromagnetic field. The interaction is continuous and local, mediated by field dynamics rather than direct contact. Another profound implication is the nature of the vacuum. If fields exist everywhere, then even empty space is not truly empty. Quantum fields fluctuate constantly, even in their lowest energy state. These fluctuations can have measurable effects, influencing particle behavior and energy levels. The vacuum becomes a sea of activity rather than a void. The idea that particles emerge from fields also blurs the boundary between matter and force. Particles that carry forces, such as photons, are also field excitations. Matter and force become different expressions of the same underlying reality. This unification simplifies the structure of physics and deepens its explanatory power. This perspective also affects how physicists think about identity and individuality in nature. If particles are not permanent objects but temporary excitations, then persistence becomes a matter of stability in field patterns rather than substance. An object exists as long as its field configuration remains intact. Change becomes a transformation of patterns rather than the motion of solid pieces. The field-based view of particles also connects deeply with symmetry. Fields obey symmetry rules that determine what types of excitations are possible. The properties of particles emerge from these symmetries. This explains why certain particles exist and others do not, and why interactions follow specific rules. Symmetry becomes the source of diversity in the particle world. In cosmology, this idea plays a crucial role. The early universe was dominated by intense fields. As the universe cooled, different field excitations emerged, giving rise to the particles that form matter today. The structure of the universe is therefore a fossil record of field behavior in its earliest moments. This way of thinking changes how we imagine the universe at its core. Reality is no longer made of tiny beads strung through space. It is made of continuous fields capable of vibrating, interacting, and organizing themselves into complex patterns. Particles are the visible ripples on an invisible ocean. Understanding particles as excitations of fields does more than solve technical problems. It reshapes our intuition. It teaches us that permanence is an illusion, that identity arises from patterns, and that the universe is fundamentally dynamic. Fields are not just the stage on which particles act, they are the actors themselves. In this view, everything we see, touch, and experience is ultimately a manifestation of field activity. Matter, light, and forces all arise from the same underlying fabric. The universe becomes a symphony of fields, with particles as fleeting notes emerging from deeper, continuous vibrations. One of the most radical ideas introduced by modern physics is that particles are not the fundamental building blocks of reality in the way we once imagined. Instead, particles are better understood as excitations or vibrations of underlying fields that exist everywhere in space. This shift completely transformed how scientists think about matter, identity, and existence at the deepest level. For a long time, particles were pictured as tiny solid objects, like miniature balls moving through empty space. This picture worked well for explaining many observations, but it began to break down as experiments probed smaller and smaller scales. Particles behaved in ways that no solid object could. They appeared and disappeared, acted like waves, and sometimes existed in multiple states at once. These strange behaviors demanded a new framework. The field concept provided that framework. In modern physics, every type of particle is associated with a specific field that fills all of space. The electron field, for example, exists everywhere, even in regions where no electrons are detected. An electron is not something separate from this field. It is a localized disturbance, a small vibration in the electron field. When the vibration fades, the particle effectively disappears. This idea explains why particles of the same type are truly identical. All electrons have exactly the same mass, charge, and behavior because they are excitations of the same underlying field. They are not individual objects with separate identities, they are expressions of a single universal field. This insight solved a deep mystery that classical physics could not address. Understanding particles as field excitations also clarifies particle creation and annihilation. In high-energy environments, such as particle accelerators or the early universe, energy can be converted into field excitations. New particles appear because fields are energized. Conversely, particles can disappear when their energy is transferred back into fields. This process follows precise rules and conservation laws, all governed by field interactions. The wave-like behavior of particles also becomes natural in this picture. Since fields can support waves, their excitations naturally exhibit wave properties. Interference, diffraction, and uncertainty are no longer strange anomalies, they are expected features of vibrating fields. The dual nature of particles as both waves and particles is unified under a single explanation. This view also changes how interactions are understood. Forces between particles are not direct pushes or pulls. They occur because fields interact with one another. When an electron repels another electron, it is because their fields influence each other through the electromagnetic field. The interaction is continuous and local, mediated by field dynamics rather than direct contact. Another profound implication is the nature of the vacuum. If fields exist everywhere, then even empty space is not truly empty. Quantum fields fluctuate constantly, even in their lowest energy state. These fluctuations can have measurable effects, influencing particle behavior and energy levels. The vacuum becomes a sea of activity rather than a void. The idea that particles emerge from fields also blurs the boundary between matter and force. Particles that carry forces, such as photons, are also field excitations. Matter and force become different expressions of the same underlying reality. This unification simplifies the structure of physics and deepens its explanatory power. This perspective also affects how physicists think about identity and individuality in nature. If particles are not permanent objects but temporary excitations, then persistence becomes a matter of stability in field patterns rather than substance. An object exists as long as its field configuration remains intact. Change becomes a transformation of patterns rather than the motion of solid pieces. The field-based view of particles also connects deeply with symmetry. Fields obey symmetry rules that determine what types of excitations are possible. The properties of particles emerge from these symmetries. This explains why certain particles exist and others do not, and why interactions follow specific rules. Symmetry becomes the source of diversity in the particle world. In cosmology, this idea plays a crucial role. The early universe was dominated by intense fields. As the universe cooled, different field excitations emerged, giving rise to the particles that form matter today. The structure of the universe is therefore a fossil record of field behavior in its earliest moments. This way of thinking changes how we imagine the universe at its core. Reality is no longer made of tiny beads strung through space. It is made of continuous fields capable of vibrating, interacting, and organizing themselves into complex patterns. Particles are the visible ripples on an invisible ocean. Understanding particles as excitations of fields does more than solve technical problems. It reshapes our intuition. It teaches us that permanence is an illusion, that identity arises from patterns, and that the universe is fundamentally dynamic. Fields are not just the stage on which particles act, they are the actors themselves. In this view, everything we see, touch, and experience is ultimately a manifestation of field activity. Matter, light, and forces all arise from the same underlying fabric. The universe becomes a symphony of fields, with particles as fleeting notes emerging from deeper, continuous vibrations. Understanding fields does more than explain forces, particles, and energy. It fundamentally reshapes how we see reality itself. The idea of a field invites us to abandon the picture of the universe as a collection of separate objects moving in empty space, and replace it with a vision of reality as an interconnected whole. This shift is not only scientific but deeply philosophical, influencing how humans think about existence, connection, and meaning in the universe. In the field-based view, nothing exists in complete isolation. Every object, from the smallest particle to the largest galaxy, is embedded in fields that extend far beyond its immediate location. These fields overlap, interact, and influence one another, creating a continuous web of relationships. Reality becomes less about individual things and more about patterns of interaction spread across space and time. This perspective changes the meaning of presence. An object is not just where it is located, its influence extends outward through the fields it generates. A star affects space far beyond its visible light. A charged particle shapes the electromagnetic environment around it. Even a human body subtly modifies fields in its surroundings. Existence becomes something that radiates, not something confined. The concept of cause and effect is also transformed. Causes do not leap instantly across space. They propagate through fields, carrying influence step by step. This creates a universe where events unfold in an ordered, continuous way. The future is shaped by the present through the evolution of fields, and the past leaves traces that continue to move outward long after the original event has ended. Fields also blur the distinction between what we traditionally call space and what we call substance. Space is no longer an empty container holding matter. It has structure, energy, and dynamics of its own. Matter and space become deeply intertwined. Objects are not simply placed in space, they are patterns within it. This challenges everyday intuition, but provides a more coherent picture of nature. This view encourages a shift from thinking in terms of static objects to thinking in terms of processes. Reality is not built from unchanging pieces, but from ongoing activity. Fields evolve, fluctuate, and interact continuously. Stability arises not from immobility, but from balance. An atom is stable because its field interactions are balanced, not because its parts are frozen in place. The field concept also reshapes the notion of emptiness. What appears to be empty space is actually filled with fields in their lowest energy states. Even in complete darkness and isolation, fields continue to fluctuate. This means there is no absolute nothingness in the universe. Everywhere is part of the same underlying fabric. At a human level, this interconnected view of reality carries profound implications. It suggests that separation is not as absolute as it appears. Everything is linked through shared fields that stretch across the universe. The same physical principles govern the behavior of stars and cells, galaxies and atoms. This continuity fosters a sense of unity between humanity and the cosmos. Fields also influence how scientists approach knowledge. Instead of seeking ultimate particles as the final answer, physics now seeks underlying principles that govern fields. Understanding becomes less about listing components and more about uncovering relationships. This relational view aligns closely with how complex systems behave in nature, from ecosystems to societies. The field perspective also alters how we think about permanence and change. Objects may appear stable, but at a deeper level they are sustained by constantly renewing field interactions. Change is not an exception but the norm. Even what seems solid and unchanging is supported by invisible motion and balance at the field level. This way of thinking extends to time as well. Fields evolve over time, carrying the imprint of past events into the future. The present moment is not isolated, it is shaped by earlier field configurations and will shape future ones. Time becomes a continuous flow of evolving patterns rather than a sequence of disconnected instants. The field concept also encourages humility. It reminds us that reality may not conform to everyday intuition. The deepest truths of the universe are subtle, invisible, and abstract, yet they govern everything we experience. Accepting this expands human understanding beyond the limits of direct perception. In science, this shift has practical power. It guides the search for new theories, informs experimental design, and connects diverse areas of research. Whether exploring the origins of the universe or the behavior of quantum systems, the language of fields provides a unifying framework. Ultimately, understanding fields changes how we define reality. Reality becomes a living network of influence, where space is active, matter is dynamic, and connection is fundamental. The universe is not a collection of isolated parts but a single, coherent structure woven together by fields. This perspective invites a deeper appreciation of the cosmos. Every action leaves a trace. Every existence shapes its surroundings. Everything participates in a vast, ongoing interaction that spans the universe. To understand fields is to understand that reality is not made of separate pieces, but of relationships that bind everything together into one continuous whole.